Hello, everybody, to our presentation of our paper, Effects of ICT-Enabled Flexible Energy Consumption on the Reduction of CO2 Emissions in Buildings, Findings and Outlook from an Explorative Case Study in Germany, written by Severin Beuker and me, Simon Hinterholzer, both working at the Borderstep Institute in Berlin, Germany, for the ICT4 Sustainability 2020, which is happening completely online this year. So you can find the paper on our website, or at least the preprint version, borderstep.org/publications. And first of all, why and how shall we do dynamic CO2 balancing, and what does this flexibility mean? So the background is that we have an increasing number of renewable energies in the power grid, so wind power and solar power. And these are leading to a variability in the power production mixture. And from there, you can derive different carbon dioxide emissions for each hour of the year, depending on how much renewables are producing in this hour. And this can be used for balancing or for accounting the CO2 emission of specific electricity appliances. And we can also use that approach for pricing and trading, and for balancing of the CO2 emissions for specific appliances, for example, in a city district, which we have done in the research project here. So here you can see the production mix of the last week here in Germany, and you see on the bottom you have biomass power production, then you have hydropower in light blue, then you have two different powers for wind power, which is offshore and onshore wind power, and you have the solar power that only happens during daytime, and then you have in brown and gray all the fossil fuels and the nuclear power production. So the mixture is very different from hour to hour in the electricity system, and this is just to illustrate how much this is varying from day to day, from day to night, and during 1 week. For our calculations in the paper and for the research project, we've calculated the CO2 emissions for the whole year of 2019 for each quarter hour, for each 15-minute interval. And you can see here 1 week in January, there is only low solar power production, but you can still see there is a huge variability in the CO2 emissions. If you, for each quarter hour, you calculate the production mixture and derive a CO2 emission curve for the whole year. This is just for 1 week, but for the whole year, you see a lot of fluctuations there. Even here, you can see like halving the CO2 emissions within just a few days. So that's also a motivation to use that approach. Within our research project, we have a smart neighborhood with 6 buildings, which consists of a lot of households, about 200, which use fridges, freezers, washing machines, dishwashers, and other household appliances. And we just considered these 3, like the fridges and freezers, washing machines and dishwashers and dryers, for flexibility appliances. And we also have some other appliances which are not considered flexible. And we have a heating supply where we also see some devices which could be used for flexibility, which is a CHP, combined heat and power producer, for on the one hand. On the other hand, we have the electric heater, which also interacts with the electricity system. And on the heat side, to have a real picture, we also need to model the gas boiler, which has direct emissions, which you can see here in the yellow arrows. And we have a heat storage, which is really important for flexibility or shifting heat production from one hour to the other. And here we have the line where we account the CO2 emissions depending on which hour they are, the electricity is consumed or the electricity is produced in the CHP. And we do that with no knowledge of the energy system over one whole year of the year 2019 and the emissions that happen there and the power plants and also the other production of renewables that do not have a lot of CO2 emissions but produces a lot of electricity. And if the electricity is clean here, for example, only little CO2 emissions are accounted if electricity is consumed at that time, but higher emissions are calculated for the consumers if there is a lot of fossils providing the electricity to the power supply. So this is the basic scheme how we did that, and as a motivation for the users of electricity, of course, there need to be a monetary incentive, which we don't have at all right now for at least for household appliances or for small consumers of electricity. But we have a smart meter rollout, which will bring new metering technologies and also the ability to incentivize the flexible energy consumption. And we have these incentives already at the wholesale market or at the energy exchanges. And you can see that here in that picture from the energy exchange in Germany. For each quarter hour, we draw 1 point, depending on the electricity mix with the CO2 emissions on that line, and also the electricity price for that respective quarter hour. And so you can see the dependency that at times of really low CO2 emissions and high renewable supply, you have really low prices typically. And at times of higher emissions in the electricity grid, you have higher prices for the power consumers. So you see there is already an incentive, but it's not passed through to the customers. But this will happen in the future. We are quite optimistic through the smart meter rollout. But just as background information, these incentives are already there, but just not passed through. So the savings that we found out for the household appliances were 1.7 tons for the washing and drying sector, about 1 ton for the dishwashers, and about 2.6 tons for the cooling and refrigeration in that district, which is actually for that amount of people that live there, about like 200 households. It's not that much, but you need to know that these savings can mostly be done without changing the behavior, like cooling and refrigeration. If you have a more intelligent fridge or freezer that can provide or lower the temperature in times of overproduction from renewables and save energy at other times without you recognizing that. And also your washing machine, at some points it is not really necessary if the laundry is ready within 1.5 hours, or it takes 2 hours or 3 hours. So, but it should not shift the laundry, for example, to the nighttime. Therefore, we've set some restrictions. Otherwise, the algorithm we've written would shift a lot of power to nighttime, or at least to times where renewables produce energy, and there is less other consumption from the industry, for example. So we've also set some restrictions, which you can read in the paper, for how many hours something can be shifted, for example. And the CO2 reduction potentials through load shifting in the heating sector, they were calculated by real operation data, which we collected through the last year, while the operation data from these appliances were calculated on average appliances of dishwashing, for example, or washing and drying within Germany. There are figures available, so we used average figures for that. But for that reduction potentials, or for that operation figures, we used the real data which we collected from the district. And the CHP has a reduction potential of 12.8 tons of CO2, the gas boiler about 22.68 tons of CO2 for that year, and the electric heater, because it is only a consuming device, produces additional CO2 emissions because it was not used before at all. So compared to not using electric heater, this will always produce some CO2 emissions, but it is only operated in times of very low CO2 emissions in the electricity grid, and this only enables us to not use the gas boiler during these hours and to avoid the CO2 emissions that gas boiler would have caused if it would have produced that heat, or the CHP would have produced if it would have run directly. So that that additional CO2 emissions enable the savings of these appliances in total, coming out to about 30 tons of CO2 per year. Our conclusions from the calculations were that traditional balancing schemes with static CO2 factors can give no guidance for electricity use because they just don't reflect the energy production side, which is in our eyes quite important to have the dynamic situation in the electricity production also reflected for CO2 balancing. And we therefore suggest the dynamic CO2 balancing, which brings us more forward to the grid-friendly consumption of electricity and the integration of renewable energies, and the controlled usage of flexibility, and to make it to better account which effect flexibility brings to the whole electricity grid. And for our district, we found out that the load shifting and adapted electricity consumption in the household appliances has some effect on the CO2 emissions, but a higher effect can be gained with the heat supply and the bigger devices that we have in the district, and they have more effect on the power production, the power draw of the overall district. So this has a bigger impact on the CO2 emissions if we use that more flexible. So thank you for listening. If you have any further questions, please just write us an email or get in contact with us. Thank you very much. Bye-bye.